Welcome to today's lesson. Standard form and significant figures. Standard form and significant figures. Let us look into the agenda today. We are going to convert ordinary numbers into standard form, and we are going to convert standard form into ordinary numbers. We are going to apply ideas to solve scientific calculations. We're going to recall and use rules for significant figures. Welcome. Significant figures. Scientists use significant figures to determine how precise a measurement is. What do we mean by this? Let's look into this. Can you see where the arrow is pointing? Somewhere between 13 and 14. What value can you read? Do you think you will be able to read 18? Or this is 13.5 or 13.6? What value can you read? Measured numbers, let's start there. The width of the door is measured as, look into that door and look at tape A and look at tape B. .8 meters. That is how the width of the door is measured. 0.8 meters for meter stick A, because the known value is between 0 and 1. If you look at meter A, meter stick A, the known value is between 0 up to 1 meters. So the known value there is 0.8. So 0.8 is estimated. Listen to this. It is estimated because we look at the meter stick from 0 to 1 and we estimate that value 0.8 to say this door is approximately, or this door is estimated at 0.8. We will of course measure the 0.77 meters for meter stick B because the known value is between 0.7, look into that, it's between 0.7 and 0.8. So the estimated value there is 0.77. So for the person having meter stick A and the person having meter stick B, it's not that any of them are wrong, but it's what is there in that meter stick that would make them to estimate a certain value. Here's the problem. Always have to estimate the final digit. That's the problem. If we estimate, it means, remember, we are not being exact. So we always have to estimate the final digit. Of course, we can't say stick A is 1.2. We will never say that. So they are all 0, but the other one is 0.8 and the other one is 0.77. And mind you, when you round off the 0.77, when you round it off to 1 decimal place, it gets you back to 0.8. Significant figures. As a result of these estimations and these rounding offs and all of that, the significant figures in a measurement include all of the digits that are known plus the large digit that is estimated. Measurements must always be reported to the correct number of significant figures because calculated answers can't be more precise than measured numbers. So, when we do measurements, we must always report to the correct number of significant figures. Example, if you are asked the average weight of the animals in the kennel or in a kennel, which is 25.2 kilograms, 24.6 kilograms, 20.1, 28.2. The average weight would be 24.5 kilograms. As we can't be more accurate than the number of significant digits given. So, we can't go over and say it's 24.52 what. We can't be more accurate than the number of significant figures. The number of significant figures is 3. So the average weight should go up to 3. That is why we are saying calculated numbers can't be more precise than measured data. The first rule in significant figures. Listen to this. Every non-zero digit is a significant figure. Whenever a number is 12, 1, 2, 7, as long as it is a non-zero, not zero, it is significant. Let's look into this. How many significant digits are in the following numbers? There are 3 significant figures in the number 274. There are 5 significant figures in the number 25.632. 5 significant figures. There's 2 significant figures because every non-zero digit is a significant figure. So there's 0 digit on 0.74 is not significant. Then the digits that are significant is the 7 and the 4 in the number 0.74. This number 0.74. 7.145. 4 significant figures. We have 4 significant figures because all of those numbers are non-zero. So remember, every non-zero digit is a significant figure. Let's look at the second rule. Zeros between non-zero digits are significant. It means that zeros that are not between non-zero, I mean, you could have seen with the 0.74, it's not between non-zero digit. So it's not significant. So what I'm saying is that leading zeros and trailing zeros are not significant. The significant digits are the ones that are between non-zero digits. Let's look into this one. How many significant digits are in the following? 60002. So here there are 5 significant figures because the 6 is significant, the 0, first 0 is significant, the third 0 is significant, this 0 is significant. Why? Because these are zeros between 6 and 2. They are zeros between non-zero numbers, so they are significant. They they are significant. 9.077. 4 significant figures. 4 significant figures. And then what do you think are the number of the significant figures in that 40.7? 40. Well, how many? Of course, you are right if you had said 3. And what do you think about the next one? 1.0012. Oh yes, you are correct when you say 5. Are we getting there now? That is the second rule when we come to significant figures. Rule number 3, which is based on rounding. Place-holding zeros are not significant. Place-holding zeros, they are not significant. Any zeros that are place-holding, they are not significant. What do I mean? I'm talking about the leading zeros and the trailing zeros. Those are the place-holding zeros. I did mention, remember, that leading zeros and trailing zeros are not significant. 4,000. 40000. We only have one significant figure. Only the non-zero number. Other zeros are trailing. They are not significant. The zeros are trailing. They're not significant because they're not in between significant figures. We have one significant figure. How many significant figures do you think we have in 0.0002? Of course, you are right. 1. Because there are leading zeros, which is 4 of them. They are not between non-zero digits. So for that matter, they are not significant. But also, you've got this number having 3 significant figures. Why am I saying that? It's because this is 6.02, of course, with many other zeros that can come after that, as you have 10 exponent 23. It's a very long number with many other zeros. But only the 3 first digits, 6.02, they're the only ones who are significant. All the trailing zeros are not significant. They can be 23, they can be 24, they can be 22, it doesn't matter. They are just not significant. This is important for standard form later on. You'll see. Converting significant figures, rounding. To round a number, we must first decide how many significant figures the answer should have. That's very important. Then we must look to the right of the last significant digit. If the number is 5 or higher than 5, we round up. If the number is 4 or less than 4, then we don't round up. I don't want to use the language and say we round down. No. We do not round up. Let's see. Round 43.82 to 3 significant figures. You'll see that 43.2 is to how many significant figures? Is to 4 significant figures. So let's round it to 3 significant figures. 43.82 round to 3 significant figures. We look at the last right number, which is 2. 2 is less than 5. we do not round up. What does that mean? It means our answer for this is 43.8. It's 43.8. What if we had 43.9? What if we had 43.89 or 43.82? What was going to happen? 0.86 for that matter. And let's see in the next example. Let's round 234.87 to 4 significant figures. What do you think the answer is going to be? You might have got it right because you realize that rounding to 4 significant figures, we look at the number 7, the most right number. 7 is greater than 5. You remember the rule? You round up if you are 5 or more. You round down if the last digit is 4 or less. Then our answer is going to be 234.99999. Rounding up. You can have this particular activity on yourself, by yourself there, where you are rounding up to 3 significant figures, 2 significant figures, and these are going to be your answers. Let's go. Hope you got all these answers until you got these two. Now let's look into standard form. Scientists created a unique way to express very large or very small numbers. And you would have seen that already in one of the examples that I provided you with. Standard form is written as follows: a number between 1 and 10. A number between 1 and 10 is followed by a multiple times x to an index or to a power. For example, 5.2 is a number between 1 and 10 multiplied by 10 to the power of -3. There is always only one number to the left of the decimal point. So you need to understand here, you cannot be having 10 point what, because the number must be between 1 and 10. So there's always one number to the left of the decimal point. There can be many numbers to the right of the decimal point. Why is 23 multiplied by 10 to incorrect in standard form? I think we all know the answer now. Remember the rule, we must have the number between 1 and 10. So you can't have 23. Any number between 1 and 10. Let's look into writing the number 93323 in standard form. Firstly, you must know that move the decimal until a non-zero number is in front. Move the decimal until a non-zero number is in front. But also remember that the decimal must have only one number on the left of it. And then you put the multiple, you multiply by 10. Count the number of decimal places that you have moved, which is 4, and place the index number. That is why that number is 3.9999923 multiplied by 10 to the power of 4. And the 4 is positive because we moved to the left. It is 4, a positive one, because we moved the decimal point to the left. And then for small numbers, you write the number in standard form. Move decimal until a non-zero number is in front. So that's standard form was 0.0052. And then a non-zero number is in front, and we put multiplication. We multiply by 10. So there's a non-zero number there, which is 5. So now it's going to be 5.2 multiplied by 10. But how many times did we move? We moved 3 times to the right. We moved 3 places to the right. So we moved from 0 to 0, 0, and 5. So 0, 0, 5. That's how we move the decimal place. 3 places to the right. If we move to the right, it becomes negative. The index becomes negative. The exponent becomes negative. 5.2 multiplied by 10 to the 3, to the negative 3 in this particular. Let's look into some examples that you can play around where you look ordinary to standard form. Let's talk about it. What do you have as your answers there? Think about it. Are you happy? There we go. That's interesting. Did you see that? That 137 billion. There we go. Students, to multiply 2 numbers in a standard notation, we add the exponents. You'll see when we deal with exponents deeply in grade 10 mathematics. So if you're having 10 to the power of m times 10 to the power of n, then you have 10 to the power of m plus n. For example, 10 exponent 4 times 10 exponent 2 is equals to 10 exponent 4 plus 2, which is 10 exponent 6. To divide 2 numbers in standard notation, as I said that we will do this mostly in exponents in grade 10, we subtract the exponents. So that becomes that. Get it? And you later see that 10 exponent 1 is just 10. And then you can go on and practice this. You can go on and practice this, whereby you work out each calculation, give your answer in standard form, and work out each calculation, give your answer in standard form. You can play around that. And you'll see that when you play around that, those are going to be your answers. All the best.